Now we're going to look at derivative rules. So these will give you shortcut ways to find slope of a tangent line, any of the other applications that we look at for the derivative of a function. Rule number 1, if f of x is equal to c, a constant, then f prime of x is equal to 0. For example, if I have a function v of t equal to 17, well, let's think for a minute what the graph of that function will look like. T is the variable, v is the function, v is equal to 17, v is a constant. So the graph is a horizontal line. Now, a horizontal line has slope equal to 0. And what was that application of derivative? Slope of a tangent line, slope of the line. So the derivative v prime of t is equal to 0, always for any constant. Okay. You have to remember things like horizontal line, slope is equal to 0. So the derivative rules are set, but you have to remember the other information that you already know. Let's think about rule number 2. If f of x is equal to x to the first power, then f prime of x is equal to 1. This is the line, y equal to x. That's what f of x is equal to. We call it the identity function because y is equal to x. And if you think of the graph of that function, x is 0, y is 0, x is 1, y is 1. The identity function, x is 2, y is 2. The slope, if you think of this, in general, y equals mx plus b, slope is 1, derivative is 1. Again, the most common way to think about a derivative is as slope of a tangent line, and so you'll need to try to remember your basic function. If I want to graph the derivative up here, the derivative was 0, that would be y equal to 0. So this is v prime equal to 0. Down here, if I want to graph the derivative is f prime equals 1. Here's 1. That's the graph of the derivative. So that we can look at the graph of the derivative, graph of the function, but basically what you have to do now is memorize the rules. If you have a function that is equal to a constant, the derivative is 0. If you have a function equal to x, the derivative is 1. Let's see about another linear function, y equals mx plus b. Suppose our linear function is f of x equal to 3x. That's a line, and it's y equal to 3x. What's the slope of the line? Slope of the line is 3. The derivative is 3. Now, this is not the identity function. This is just a linear function. And you all know what lines look like. So we can graph that line. Y equals 3x. If x is 1, y is 3. X is 0, y is 0. Steeper. And my derivative in this case is equal to 3, which is a constant horizontal line. F prime of x is equal to 3. So we have an identity function, f of x equals x, derivative is 1. We have a linear function, but notice that we're just looking at the linear function y equal to mx. We're not dealing with any constants now. Just here's mx, here's the slope, that's the derivative. Now let's look at the example where the function is just y equal to 1 over x squared. Now there's an x squared, however, it does not fit the form because you have to have the function in the form f of x equals x to the n. But I can rewrite this because of the exponent rules that everybody has to know and remember. If I want to rewrite this as x to a power, it's just x to the negative 2. And then I can take the derivative. So y prime would equal, bring the negative 2 around front, times x. And then when I subtract negative 2 minus 1, okay, I get negative 3. So my derivative is negative 2 times x to the negative 3. Most of the time, we don't leave negative exponents in answers. We try to put them back in their regular form. Negative 2, and this part would be 1 over x cubed, just like it started off as 1 over x squared. So it's negative 2 over x cubed. So that's the standard way to continue to simplify the problem. How about f of x equals the square root of x, another radical. This one appears often. This radical is more basic than the previous one. This is just x to the 1/2. Whatever the root is goes on the bottom. So the derivative, f prime of x, is 1/2 times x. And here when I subtract 1, 1/2 minus 1 is negative 1/2. And we can simplify this similarly to what we did up here. I have a negative exponent, so I have to bring it to the denominator. So I'll have f prime of x equal to 1/2 times 1 over x to the 1/2. Negative exponent just moves it to the bottom with a positive exponent. And I can write that as 1 over 2, and then this is the square root of x. Now, back when we were doing rates of change, we would find the derivative at a point, and would have to pick a number on either side of our point of interest and do the slope. Now, if I want to find the derivative at x equal to 3, I can just write f prime of 3 equals 1 over 2 times the square root of 3, and find the value for it if I need a decimal value. So it's a lot simpler to use the derivative rule, and then you just plug in your point. You don't have to do any testing on either side. Let's do one more power rule problem. Y equals 1 over the 4th root of x. So we have a radical and a fraction in this one. And notice I'm finishing my simplification into the form x to the n before I go to the derivative notation. It's very important that you watch your notation. This would be 1 over x to the 1/4. For the derivative rule, I have to bring that up to write this as x to the negative 1/4. And then I can take the derivative y prime. We could also write this as dy dx. Exponent comes around front times x, and I have to take negative 1/4 minus 1. 1 is 4/4. So this would equal negative 1/4 times x to the negative 5/4. And that looks really complicated. Let's see if we can simplify that. Sometimes rewriting and simplifying are two different things. 1 over x to the 5/4 doesn't really look simpler, does it? Equals negative 1 over 4 times the fourth root of x to the fifth power. I kind of like that one better. So you just need to be able to get from one step to the other to get your answers to look the way you can recognize them or somebody else can recognize them. Okay, let's move on to the next derivative rule. The next derivative rule is rule number 4. It is about the natural exponential function. If f of x is equal to e to the x, then f prime of x is equal to e to the x. It seems very odd, but this is the case, which is why we use natural exponential function so often in calculus, because the function and the derivative are the same thing if it is just e to the x power. Remember, an exponential function has the x as the exponent and the e as the base. E, remember, is a number. E is about 2.71828, ... So e is a number, and it's an exponential function, so x is in the exponent. How about if I want to find the value f prime of 2? Then I would take e to the second. And that's a decimal value. It's about 7.389 if I round it to 3 decimal places. So again, if I take a derivative and I want to value at a point, I just plug the point in. Now be careful. Suppose your function is f of x equal to e squared. This is a constant function. It's not an exponential function because there's no x in it. I have f of x here, but no matter what I plug in for x, there's no x to put the number in. So the derivative of this function is 0. Remember, the derivative of a constant function is just 0. Now, I did not look at graphs when we were looking at the power rule because the powers vary so much. But the exponential function, that's one of those graphs that you're going to want to remember. If x is equal to 0, e to the 0 is 1. If x is equal to 1, e to the first is about 2.7. So it's up here somewhere. And this is the function that has a horizontal asymptote down here at y equal to 0. Horizontal asymptote. Y equal to 0. So the general shape of the exponential function e to the x is this. Now, if your exponent is negative, that changes everything. This is the basic shape of the graph. So this is something that you want to remember. The basic shapes of the functions, a parabola is a quadratic, it's square, it's a power function. So keep in mind what your functions look like. Let's look at the next exponential function. Rule 5 is the general exponential function that's not base e. If f of x is equal to a to the x, where a is a number. A is not equal to 1. Okay? Then f prime of x is equal to natural log of a times a to the x. So basically, it's like the e to the x function, where the derivative of a to the x is a to the x, but because it's not base e, it's not natural, you have to multiply it by the natural log of the base. If we have the function f of t is equal to 3 to the t power. If I take the derivative of that, f prime of t, you just follow exactly along what the rule says. You just memorize it. Natural log of the base, so that would be ln of 3 times the function, 3 to the t. So the function is always in the derivative if you have either exponential function. If I have g of x equal to 23 to the x, and I want to take the derivative of that, I just do the rule. G prime of x is ln of 23 times 23 to the x. And we tend to write them with parentheses in all kinds of different places. The ln of 23 has to go together. There's always a number with an ln or a variable. Now, here's something to watch out for. Suppose my function h of x is 3 space 5 to the x. In a lot of math software, a space means multiply. Note the difference between 23 and 3 space 5. If I take the derivative here, the 3 stays. This is not a linear function, but think about it as if I had a linear function, g of x equals 3x, my slope would just be 3. This is the same type of thing. We'll get specific examples of this constant multiplier later, but this is something to start looking at now as an example of this space that may happen. So this derivative, 3 is a constant. To take the derivative of 5 to the x power, the derivative said you need ln of 5 times 5 to the x. So all of that is the derivative. Now if I want, say, h prime of 3, I'll have 3 times ln of 5 times 5 to the third. 5 to the third is 125. Multiply that by 3, you get 375 natural log of 5. That is the derivative at the point where x is equal to 3. That pretty much takes care of some of the complicated parts of the exponential function. The natural exponential function is more straightforward. This one's a little more complicated. The last rule for derivatives that we have to look at here is Rule 6, natural logarithmic function. Also called the log rule. If f of x is equal to natural log of x, then f prime of x is equal to 1 over x. Sometimes in math software, ln will be written as log with no base. So this could also be if f of x equals log x, then f prime of x is equal to 1 over x. And in the place of the general exponential formula, if there's an ln of 3, there could be written as log of 3. You may be more familiar with this standing for log base 10, but not in math. So if it's any other base, you'll see the base written. Most of the time, it'll just be natural log, but it could be written as log. So if I have a function f of q equal to natural log of q, then the derivative f prime of q is 1 over q. It's kind of nice. Most people don't like working with natural logs, and then if you take the derivative, it's not a log anymore. But remember, this is the derivative. The function does not equal 1 over q. The derivative of natural log is 1 over q. Suppose you just have f of x equals 1 over x. Is the derivative natural log? No, think about that. This is x to the first in a denominator. we can rewrite this as x to the negative 1. It's a power function. So we need to use the power rule. So the power rules to find the derivative says bring the negative 1 around front times x, and negative 1 minus 1 is negative 2. So this is negative 1 over x squared. The negative exponent just moves the x to the denominator. We saw what the derivative of the natural logarithmic function was. Let's think about what the graph looks like and talk about the domain of the function. If f of x is natural log x, and we've studied natural log function before, just a reminder, if x is equal to 1, the natural log of 1 is equal to 0. So if x is 1, we have our point here. Now when we talk about limits, we talk about plugging a lot of numbers in to see what a graph looks like. And if you plug in fractions for the natural log, you get numbers that are negative and get increasingly large as you get closer to 0. And then when you hit your positive numbers greater than 1, the graph increases very slowly up this way. Never goes down, it just continues to increase. So when we talk about the derivative of the natural log function is 1 over x, you know that x cannot equal 0 here because it's in the denominator. The same thing here. X cannot equal 0. And actually, x cannot be negative. So knowing a little bit about a graph can help you when you start trying to plug numbers in. You cannot do natural log of 0. It doesn't exist. You can get close to it. This is actually a vertical asymptote at x equal to 0 for the log function. So we can't put in 0 or anything less than that when you actually start doing your substitution.